Hey guys, welcome to System Design Fight Club. Today I'm going to be going over most of what I know about database indexing. This is a topic that I've wanted to do for a while, so I'm pretty excited to finally get a chance to cover it. What we have here at the front is a list of all the things that I'm hoping to cover in this video. Along the left are some visuals that I'm hoping will really help when I'm trying to explain some of these concepts. Hopefully I'll get around to adding some chapters or key moments or whatever it's called to this video so that it gets much easier to click around for whatever concept you're most interested in hearing about. Otherwise, this is basically the end of the script that I've actually written out for this video, and video editing takes a tremendous amount of time, which is why I don't do that. So the video is about to get a bit more clunky. Most of what I know about this topic comes from the following resources: Designing Data-Intensive Applications by Martin Kleppmann and Database Internals by Alex Petrov. This is kind of going to be relevant a little bit later in the video. I've also had to read a lot of documentation on specific databases to figure out certain things, like what databases support what features, why those features even make sense. There was a few that aren't even covered in these books, such as vector indices, skip lists. So that's why I felt compelled to even make this video. I'm not just going to summarize those books and make a video about it. That's lame. We're going to add a little bit more that aren't covered in those books. So there's two key concepts that I think are going to be really important for setting some context for the types of indexes that I'm going to be covering. The first one is the RUM Conjecture. You can read about it in Database Internals by Alex Petrov. It's the best thing that I think covers the RUM Conjecture. I actually couldn't even find a Wikipedia article about the RUM Conjecture. It has, I think it came from a paper, an academic paper. There's a whole academic paper about it. It's this really obvious concept, but like you don't, it's one of those things that like after it's explained to you, it like really helps to think about stuff, but it's like super obvious. It's kind of like CAP theorem, but for indexes. So RUM stands for read, update, memory overhead. And you have to make a trade-off between the speed of your read operations and the speed of your write operations. You can kind of do a little trade-off involving memory overhead. That's a little bit of a in-between on those. An example of that is with LSM-Trees, where your write operations are super fast. They just go straight to disk, just an append to file. They're very fast, but then you have all this extra space wasted at the end of this file. It's just kind of sitting around. So that's where you have this wasted memory by trying to make your read operations a lot more fast. I think I'd already said that there isn't really a Wikipedia article on RUM Conjecture. The best resource for finding stuff about it is on Database Internals by Alex Petrov, or maybe the academic paper on it. The second concept, you might have read, you might have seen this before if you've read Designing Data-Intensive Applications by Martin Kleppmann. It's that a database is basically a write-ahead log with a materialized view. For example, Kafka can kind of be thought of as purely a write-ahead log. If you were to add indexes to Kafka, you're kind of turning it into a database. The fastest way to do write operations in a database is if you have no indexes at all, if you just have the write-ahead log on its own. It's a really insightful way to kind of view databases, is that you just start with the write-ahead log and then you can kind of add these indexes over top of it as a materialized view. So that's also kind of why the first type of index that I want to cover is no index. So if you don't have any indexes at all, you just have the write-ahead log. That's all that's left. That's the fastest way to do a write operation. That's why I wanted to cover it, is that like I said with RUM Conjecture, whenever you add a index, you're making a trade-off of increasing the amount of time that it takes to perform a write operation. Whenever you add an index, that means that every time you're trying to add a new record, there's a little bit of extra processing time that needs to be used in order to update all of the indexes that it's going to be included on. So the fastest way to do a write operation is if you don't have any indexes at all. And so that's why Kafka is really fast at handling write operations. There's no indexes on it. Data warehouses also don't really have indexes. So when you add these indexes, it speeds up your record lookups. If you're trying to look up a individual record, you're going to have like a log of in access, but typically when you're working with data warehouses, it's OLAP queries, and you're just doing full table scans anyways. So you don't really need to have really fast lookups of individual records, because you're just going to go ahead and scan the full table anyways. In some cases, you might add a materialized, an actual thing called a materialized view, and we're going to maybe talk about that a little bit at the end. I'm not super familiar with those materialized views, but usually when I've done something with a data warehouse or with OLAP queries, it just kind of pulls out the entire file and it just kind of scans over the whole thing. And so they actually just kind of typically forego the use of indexes entirely, and then they just do something a little bit alternative where they have the column data storage, where it's really fast at doing those full table scans over a record, over a column. So you would maybe like filter the full table over specific ranges for the value. And so you're just scanning down the full table along one of those columns. And so then the column access is really fast, but you don't have any secondary indexes because you're not doing individual record lookups. When you're doing something like a Spark job, I'd imagine that it might be doing something to have these other auxiliary data structures in memory, I'd imagine, but like on disk, it like pulls stuff into memory, and so like the on disk storage is just going to be column R. It's not going to have any secondary indexes there. Well, that's my coverage for no index. For primary keys, we're of course going to talk about it in a distributed setting as well. Primary key is a partition key plus an optional sort key. The partition key is basically what node that you're going to put the record onto, and then that also helps for retrieval, because then it's going to know what node to pull the data off of. Picking out a proper partitioning key is really important for making sure your key range queries are really efficient. I have some diagrams over here to kind of show that with key range queries. So it's like if you don't pick out a proper partitioning key, you get this like scatter gather that's not really performant. I have a whole video on this that's 100 seconds long and a lot more well laid out. But partitioning keys, very important for picking out for optimizing the performance of your key range queries. I did actually kind of have some examples for that. So traditionally under, so let's say that we have a posts table for a social media website, something kind of like Facebook, but not necessarily such huge volume. And you don't really have a celebrity issue, so this schema might kind of make sense. When it's under a single node setup, you would be able to do an auto increment like this. And you can just have, when you have the whole thing on one node, it's possible to just co-locate all of the records. And so then you're able to just go ahead and use a primary key right here. But when it's distributed, you're not actually able to do an auto increment, and then your primary key, so you can't do an auto increment in a distributed database. That would require total ordering. That's why you can't do an auto increment in a distributed database. Well, you can if it's linearizable like Spanner, but that's also really expensive. And so usually you try and avoid having to do a total ordering by just dodging the need for an auto increment. You just get rid of the auto increment, and then you just have UUIDs instead that look like this. And so then you can still use this as a primary key, I guess, in a distributed setting. And so if you're going to do hash partitioning in a distributed database, you can go ahead and use post ID for that. And it would still know like what node to go to for the write operation and for the read operation. But your key range queries, like I said over here, for how it looks under hash partition, you now don't know what node that a specific thing might live on if you're doing a key range query. So if I'm trying to retrieve like all of my own posts on, so like let's say that I'm doing a view of my own account's posts. So it's like if you go to my Twitter account or something like that, then you would want to have all of my posts come up, and those might be on a bunch of different nodes. So that's why it looks like this under a hash partitioning. So that's actually really inefficient. You want to avoid doing that scatter gather like that. And so that's why you would pick out a partitioning key of this. And then that's not uniquely identifying. You need to have a sort key as well. And so your sort key can be something like this one. And then you have your uniqueness constraint satisfied. And then when you're doing a key range query for a specific user, you would have it all servable off of a single node. And you have your uniqueness constraint satisfied. So you'd also be able to look up individual posts. So like with Twitter, for example, sometimes news articles will do this thing where they show a specific tweet. And if you click on that tweet, it'll pull up a page that consists solely of that singular tweet. And so then it's not doing a key range query, it's doing a single record lookup. And so you don't have to, under that scenario, hash partitioning works just fine, but the fact that you still have the user profiles is why you would typically want to use a partitioning key so that you can serve up those key range queries really efficiently. Yeah. Okay. Was there anything else I wanted to cover for primary keys? Oh, well, so there's a second sort key that we could have used here. We probably could have used the timestamp as the sort key unless we allowed users to post 2 tweets in the same millisecond. So I mean, maybe we'd have some kind of rate limiting. It'd be kind of hard to properly enforce that without having a linearizable database. So the safer thing to do would probably be to just go ahead and go off of post IDs because you can go ahead and generate a UUID properly. But this is a good candidate for like a secondary index, for example. And we'll talk about secondary indexes a bit more later in the video. I think first I want to talk about KV stores. So KV stores actually use a hash table in RAM. Typically, when you're working with a cache like memcached or Redis, I don't actually like using Redis for this example because typically your cache is not going to support secondary indexes and it's not going to support persisting to disk, which Redis does. Redis used to just be a cache, but now it supports all these crazy things that are used for regular old databases. So memcache is a better example of this. It's entirely in RAM. I'm fairly certain they're not pulling a Redis and just doing tons of crazy features. I'm pretty sure it's just a plain old key store. Usually caches don't support any secondary indexes at all, so it's entirely in RAM. I was actually really curious about why there aren't any persistent databases that also support this like hash table thing. Apparently hash tables don't work on disk. So with a btree's log of n lookup, a hash table's big O of 1. So it was like, why don't you support having a hash table style index on like DynamoDB or something? Apparently hash tables just don't really work on disk from what I've heard. But they're much more efficient than btrees or LSM-Trees. The most efficient way of looking up a record, big O of 1, that's a hash table. You can't have it with disk apparently. You can't have it on a hard disk. So that's why you can only find that with like memcached or Redis. And I thought that was really fascinating. And since the lookups, so like I said with memcache, usually caches don't support secondary indexes at all. So you're only going to be able to support single record lookups where you specify like the full primary key in order to retrieve the full record. And because of that, you don't have that concern that you would have with key range queries. You don't have key range queries really on caches, to my understanding. So it makes a lot of sense to actually do hash partitioning, I think, most of the time with caches. With Redis, you might do some other things because you might be taking advantage of indices, but I think with caches, you would usually want to use a hash partitioning strategy because you're mainly just doing single record lookups because it's a key value store. You're looking up a specific key for a specific value, so you can go ahead and use hash partitioning almost all the time with those. And then that brings us to the traditional indexes that you're going to see talked about the most. B trees and LSM trees, these usually apply to the primary key. You usually see those more rare types of indexes when you're talking about the secondary indexes. So like R trees, inverted indexes, those usually apply a lot more to the secondary index. The primary index. This is what's used by default for your primary keys. If you're not specifying something else, you're usually going to get either a B tree or an LSM tree. And the default tree that's used is going to depend on the implementation internals of your database. So for DynamoDB, the storage engine that it uses is actually going to use B trees. I don't know what the specific storage engine that uses is called, whether it's like InnoDB versus like Wired Tiger or something like that. But I do know that it currently uses B trees. For other databases like Cassandra, it uses LSM trees. Spanner also uses an LSM tree. I actually was a little surprised by that. I thought it might have used a B tree, but LSM trees were actually, I think, kind of invented at Google, so it does kind of make sense that most of their databases, like Spanner, are going to be using an LSM tree as well. This is like, these are the default indexes that are going to be used by your database if you don't specify anything else. And it's usually what you're. I don't think you can get any of the weird types of trees for your primary key. I don't know if you can actually get an R tree for your primary key. It's typically going to be one of these two. One of them is, so B trees are actually read optimized. So we see that RUM Conjecture coming up here is that one of them is more optimized for read operations, while the other one is more optimized for write operations. B trees are the most efficient. It's the most efficient way to look up a record for read operations, while for LSM trees, it's a simple append to file, like I said earlier, and so it's a lot more optimized for writes. There's actually more tuning you can do within B trees and LSM trees that actually are doing more fancy stuff with that trade-off between read latency and write latency. So for B trees, for example, you actually have BW trees. There's a few others. They're described in detail in database internals by Alex Petrov. I'm not going to go over them here. So like, I can't specify to DynamoDB that I want to use a BW tree or like a B plus tree or B star tree or whatever they're all called. So I'm like not really able to pick which of these I'm going to use. I do know that it's going to vary depending on what storage engine that you use. So I think MongoDB, for example, has this variation of B trees where it like buffers the writes, which is really interesting. But like I'm not able to specify that within like which database I'm using. I can't specify that to DynamoDB, and I think that the trade-offs between like a regular B tree and like a BW tree are not going to be significant enough to really force me to switch from DynamoDB over to MongoDB. So that's why I haven't really studied it myself a whole lot. If you're really interested in like rolling your own database from scratch, you'd probably want to like look into that a whole lot. And again, Database Internals is probably the best book for that. I couldn't find that kind of details in any of the other books that I've been reading so far. And then LSM-Trees also do have some kind of tuning that you can do in terms of like the rate of the compactions that it does. Again, it still is an LSM tree. It's not doing. It just has a different layout to its files than the way that B trees do, and so you're just really not going to get the same kind of read speed that you would with just using a B tree. But there's options for trying to tune it a little bit. I've never personally done that, and I haven't heard of anybody that I haven't seen any like company blog posts that really emphasize doing that kind of thing. Okay, I'm trying to figure out if there was anything else that I wanted to cover before going over secondary indexes. Oh, yeah, I don't know if I fully covered this while I was talking about the example with the different partitioning strategies, but so if you're specifying a partitioning key and you want to do hash partitioning, if you're trying to do hash partitioning, this is what you'd use as the partitioning key. Well, if you're trying to do range partitioning, you would use this. as the partitioning key. If you're trying to just, that's under the use case where you're trying to view a specific account's profile with all their like tweets or all their Facebook posts. It's range partitioning because it pulls up all of their posts off of a single node. You're able to service it like this. While if you were using this as the partitioning key, that's hash partitioning, and so it doesn't know which specific node all the posts are located on. They're actually probably spread across multiple, and so you're going to get this scatter-gather pattern. This is detailed a lot in designing data-intensive applications, I believe. It's kind of, I think it's over in like the 4th chapter. It's the one after where he talks about B-trees versus LSM-trees. I think it's the partitioning chapter. Okay, I think we're good to move on to secondary indexes. So this is where that link from W3 Schools was really relevant. It doesn't just index, like you don't have a secondary index on all 4 of these fields to begin with. You have to specify it using something like the create index statement, which I usually send people this link when they hear me talking about secondary indexes, that it's even a thing that you have to specify. Yes, if you want to have a log of in lookup on, so for example, with inverted indexes, if you're trying to find all the tweets that include the word coffee, you're going to have to add a inverted index over like this field. You are able to do that in PostgreSQL as well. It does support inverted indexes. We're going to go over that again towards the end. But if you wanted to be able to look up all of a specific user's tweets that include a specific word, you have to add a secondary index there. It's not there by default. And there's special syntax specifically for doing that. It's not indexed by default, though. You have to manually add secondary indexes. For DynamoDB, it supports up to, I think, like 30 secondary indexes. It supports up to 30 local secondary indexes. It supports, I think, like 8 global secondary indexes. I'm going to talk about the difference between these two things a little bit more later on. But secondary indexes, it's extra stuff. We're trying to speed it up. So, for example, if you're trying to add pagination, as in like a paged view of a person's tweets where they're sorted chronologically. So for example, you have the tweets that I sent in January, and then you want to look at the tweets I sent in December, and then another month back. You'd be sorting them by the timestamp. And if you want to make that a lot faster, you would go ahead and add a secondary index over this field. And if you don't specify what type of index that you want to use, like R-tree versus any of these other fancy ones like an inverted index, by default, it's going to use whatever's built into the storage engine. So if I think PostgreSQL might actually support using a different storage engine that is an LSM-tree, but the default storage engine of PostgreSQL is definitely one that uses B-trees, to my understanding. So that means that whatever you specified as the primary key is going to use a B-tree, and then when you add a secondary index, that is also going to be a B-tree, as opposed to Cassandra, where the LSM tree is what it uses for the default type of index. So in Cassandra, this would use, it'd be the sort key that uses an LSM tree. This one is just what node it's on, so the sort key is going to be what uses an LSM tree. And then if you wanted to add a secondary index for the timestamp, that one is also going to be an LSM tree. So whatever the default of the storage engine is what it's going to use by default for the secondary indexes. But you are also able to specify, so in PostgreSQL, if you wanted to add a R tree over a couple of different indexes, a couple of different keys, you can actually specify that would be an R tree. But if you don't do that, it's just going to use the B tree by default. And I'm also going to talk about concatenated indexes in a bit, and that'll be interesting. I'll just leave it at that. So I mentioned that the indexes are usually local. So by default, your secondary indexes are going to be local secondary indexes as opposed to global secondary indexes. So that's also what's kind of going on here with the key range query, is that you can actually kind of if you have data that lives on a bunch of different nodes that you're trying to retrieve in a key range query, You can go ahead and do a global secondary index on that, and then it does actually speed it up a lot. And so you don't really have that issue with the scatter gather that you get under hash partitioning, but it requires something that's a lot more intensive for the write operations. You actually have to go ahead and write to all of the, to my understanding, you have to write to all of the nodes in order for the global index to work. That's kind of like the difference between a local versus global secondary index, is that the local index is just a B tree that's on that specific machine, and it only has data about that one specific machine. For a global secondary index, there's data about all the records basically on all of the machines, from what I've heard. And so in order to add a record or update a record, it has to send updates to multiple machines. So if you're updating just one record, it still has to write to multiple different machines in order to update the global secondary index. And so that requires that's going to be very expensive for your write operations. It's good for your read. So again, we're seeing that RUM conjecture at play here, is that you're able to speed up your key range queries for the reads by adding a global secondary index, but it's very, very expensive for your write operations, which is why you don't really see it in practice. I've definitely not really seen this brought up in a lot of use cases, because it only really makes sense for cases where it's read heavy with a lot of key range queries, and you're not able to avoid the scatter gather. Usually you're able to avoid the scatter gather by picking a proper partitioning key. So like with this example, we were able to avoid a scatter gather, and that's what you usually see. If for some reason you're not able to avoid that, it might make sense to do the global secondary index. But another alternative is that you can just do multiple read optimized views of a database. So you would have your primary store, and then you would just have multiple different downstream versions of it that are partitioned in different ways. And so then depending on the type of key range query, like whether you're trying to look at paginated stuff by chronological order versus stuff by, I don't know what else it would be, but like by content, or if you had some other thing that was weird, location, I guess, you could go ahead and partition by location on some other secondary downstream data store. And then if you're trying to look at tweets from a specific location, you could go ahead and like read off of that or something. So it's rare that you would actually want to go for a global secondary index. It doesn't make sense in a lot of cases. I have yet to really find a case where it would make sense and you can't just do read optimized views instead. It's interesting. They are implemented in DynamoDB. Like I said, it supports up to like 8 global secondary indexes. I think Spanner supports it as well, but it just like doesn't make sense very often. So it's like a very fascinating feature, and I'm actually like, I kind of have it's not a huge goal for me, but like I'd like to find a use case where it like totally makes sense, like provably makes sense to use a global secondary index. And it's kind of tricky, but they're worth bringing up because it's a type of index. Okay, is there anything else I wanted to cover for secondary indexes? I have like these other notes off screen. Oh no, I did cover that. Okay. Yeah, and then I don't have anything that like showcases. I literally can't think of a use case where global secondary indexes make sense. All right, multi-dimensional indices. So let's say that our tweets also had a latitude and longitude. So we have latitude, longitude, and you can do, let's say it's like negative 47 degrees. And then we have, they're located at 32.78. So if you're trying to have it, if you're trying to look up tweets from around a certain location under a concatenated index, it just kind of appends them one after the other. And so those are, it has like a B tree where it's sorted by latitude and then longitude, and you're not really narrowing them both down at the same time. Some examples of concatenated indexes are actually with our primary key. So in the case of if you actually went back to that single node setup, where I was talking about an auto increment, if you did have an auto increment of say 4, 5, 6, 7 is the post ID because you're using that auto increment, and you're trying to do you're trying to create a primary key, you could go ahead and have it as you could have your primary key as like user ID comma post ID. There's cases where you like need extra things in order to like fully specify to fully fill the uniqueness constraint. Sometimes you have to use multiple columns to satisfy that uniqueness constraint. So then you make a concatenated index where you're narrowing down by one attribute and then another, and combined. Maybe the two different columns do not individually provide uniqueness, but combined they do provide uniqueness. And so you concatenate them together. It's kind of like if you were to just make another field called primary key, and it just consists of my user ID concatenated to my post ID, like as a string concatenation, just like that. So that's basically what a concatenated index is it's sorted by, if all the records are sorted alphabetically, I think that's usually how you do that with strings. If you're using a B tree rather than a inverted index, it's going to narrow it down alphabetically, and so it's sorted first by the username and then by the post ID. So that's concatenated. It's not narrowing down by both at the same time. You are actually able to narrow down by two attributes at the same time. And the most classical example of that is if you're doing geographical queries with latitude and longitude. There's a bunch of different ways that you're able to do it: R trees, quad trees, Geo-Hashes. I really like R trees for some reason. They're built into PostgreSQL. I don't know. It just has some kind of like je ne sais quoi to it. I like R trees. Geo-Hashes have some kind of issue where I don't want to go over geographical indices in detail. There's plenty of resources out there for that, and then I would just be quoting them. I think Alex Shu's Volume 2 book actually kind of talks about the trade-offs of these different things, but it's something to be aware of. And so quad trees I thought are only two-dimensional, while with R trees it's much higher dimensional than that. You can support narrowing down by 3 like different attributes at the same time, or even like 5. It's really fascinating. You're able to support it's geographical data is the most common use case for these multidimensional indices, but you are able to do like 3 or more different attributes for the narrowing down. And so if in PostgreSQL, if you're trying to do the create index for something that has geographical data, you would use that create index syntax. And I don't think it actually specifies how you would clarify which type of tree that you want to use. But you would just have something like, here, I'll go ahead and share. So if we were trying to do GeoIndex, where we have latitude and longitude, you're able to specify R tree in there. And that's actually how you do that, is that you specify that you want to use an R tree. Otherwise, it's going to use a B tree by default. So when you're trying to use an R tree or an inverted index with PostgreSQL, it does support those. You you have to specify that you want the R tree or the inverted index. Otherwise, it's going to use a B tree, and it's just going to be a concatenated index instead. You have to specify the type of tree if you want to use the special ones from the secondary index options. Okay, I think we're good to move on to inverted indexes. Also, when you're using the multi-dimensional indices, if you have a use case where you need to use one of these fancy indexes, so if you have geographical data, that's actually going to limit your database choices. So if geographical data and having really performant lookups of geographic data is important for your use case, you can't use DynamoDB actually. I don't think DynamoDB supports any type of multidimensional index. PostgreSQL supports R trees. I brought that up multiple times. Elasticsearch supports quad trees. Redis has Geo-Hash. I didn't really come across a lot of other databases that support these things though. There's probably a couple, but it was I didn't really dig that far into it. I'm not going to spend all day trying to find databases that support the multidimensional indices. Like if it comes up in like an interview that like, oh, so we're going to be designing Uber. I want to use a quad tree. I feel like it might be fair game for your interviewer to go, okay, what database? Like what are you like? Are you going to roll that yourself? Are you going to roll quad trees yourself if you're designing Uber? I don't think that's reasonable unless you're. In most cases where you're dealing with geographical data, it's not so core to your business, or your business is not large enough that it would be financially feasible for you to just roll your own quad tree. So instead, you would want to find a database that already has that implemented. So like if my own team at Amazon was dealing with geographical information for whatever reason, it wouldn't be such a key part of how Amazon works that we would be like, okay, time to roll our own quad tree implementation. No, instead we would use OpenSearch, which is like built on top of a really old version of Elasticsearch. And so it's like, oh, geographic data, and it's actually, this is going to be hit a lot. It's going to be, it's going to have like 100,000 TPS. Okay, we should probably make sure this is efficient. Let's use Elasticsearch. That's why I care about knowing about these implementations, is that I like to be kind of realistic. And yeah, you shouldn't be rolling quad trees yourself unless you're actually, working on Uber on the geographic systems. I think I've gone on about that enough. We can talk about inverted indexes now. Yeah, so inverted indexes, you're also not going to find those everywhere. You're not going to find that in DynamoDB. I don't think that supports an inverted index. Elasticsearch is what is most known for supporting inverted indexes, but you actually aren't forced to use Elasticsearch. There's actually a couple of other options. PostgreSQL supports it. I'm fairly certain Redis supports it. I'm going to go ahead and link this file in the comments like I usually do. Redis supports it. PostgreSQL, you don't have to use Elasticsearch. So what's great about PostgreSQL supporting it is that if you were going to do that manual partitioning trick that I've probably done in so many videos, you can do the manual partitioning of PostgreSQL, and then you can have your very efficient key range queries plus an R tree or an inverted index. So you can do your manual partitioning strategy and have an inverted index. So I don't know how well Elasticsearch. I'm using Elasticsearch at work, and I don't know how well it really supports various partitioning strategies. It's wonky in its own ways, and it doesn't necessarily have everything that you want. PostgreSQL has a lot of features though. It also has R trees on top of inverted indexes. So I mean, if you're using Elasticsearch and you want an inverted index, you also have geographic data. So it's like tweets with geographic data, and you want to find all the tweets that have the word coffee within Seattle's geographic location. You'd be able to use Elasticsearch with a quad tree, and it supports inverted indexes. You can also use PostgreSQL with an R tree and an inverted index because it supports that. With Redis, apparently also supports inverted indices, and then it has Geo-Hashes. I don't know if it supports, I don't recall Redis supporting either of these things, so you would maybe not be able to use Redis for that use case. And inverted indexes are also really fascinating because Google.com actually is a gigantic inverted index. They don't use Elasticsearch. They, of course, roll it themselves. They have their own home-rolled inverted index. It's gigantic. It would not work well under Elasticsearch. I think I'd recently heard that GitHub even had kind of outgrown their own Elasticsearch setup that they were using for code search. Maybe if I find the link to that, I'll stick it in the description or something. But sometimes you can be too big for using Elasticsearch, and so you might just roll it yourself like Google.com does. Otherwise, if it's something smaller, I don't know if Twitter's too big for Elasticsearch, but if you're trying to look up text, if you're trying to support text search on something smaller than Google.com, which is the majority of the internet, you can go ahead and use Elasticsearch for that, or PostgreSQL. It just kind of depends on what you're trying to do with your database and the specifics of whether it's more read heavy or write heavy. So if it's a bit more write heavy, I don't know if Elasticsearch would be so great for that. I don't know. It depends on the use case. But it's important to have multiple options, that you're not just strapped to Elasticsearch. And then going back to our example, so you can form an R tree over 2 locations, and that would look really interesting. Secondary index, R tree, and you can do another another index over here. So you have a secondary index, and you would have to specify, that it is a inverted index. While with timestamp, you don't have to specify anything. You'll just go ahead and give you a B tree by default. I'm going to delete this. Okay. So I think we're good on covering inverted indices. We're getting on to the much more rare stuff. So for example, skip lists, very niche, very niche. It's, there's only like one access pattern where it makes a lot of sense to use a skip list. Gaming leaderboard. Alex Shu has some great coverage on that use case. I've only heard of it implemented in Redis. I don't know anything else that implements a skip list. I don't know if it's because it's one of those things just like key value stores where you can't have a hash table on disk. I don't know if you're able to have a skip list on disk. If you're not able to have a skip list implemented with disk, then that would make sense. That would be why nobody else has a skip list. But it's for certain cases, I think I was even able to find at least one other thing where a skip list would be really helpful as an access pattern, but I can't think of the problem right now. Maybe it was get active events. Yeah, I think get active events, there was one variation of it where skip lists seemed like it would maybe help a lot. But it was like, okay, now I'm forced to use Redis, and I'd prefer to only use Redis as a cache. I don't know why Redis is implementing so many weird things. And Redis has a lot, but it doesn't have everything. And just being stuck with this one solution is not great. It'd be great if there were other options there, but like for the one case of where you need this weird access pattern, like the one present from Gaming Leaderboard, it like really calls for a skip list, and like you only have that in Redis. I'm not going to go over the internals of a skip list. It's really interesting. It's kind of like a linked list with like linked lists that allow you to skip over chunks of it. I'm not going to draw the whole thing out. There's other resources that probably do that pretty well. So I think we're going to move on. Vector indexes. So This is another one that's really niche. You can find it in Pinecone, Facebook's Phase. I don't know if it's pronounced like that. So these things are specifically created for being a vector database, and so then they support vector indices. It's kind of been really hot over the last year. They're useful for machine learning problems. They're very crucial to machine learning problems. Actually, I think it's not just ChatGPT where these are useful. It's basically, it seems like they're useful for basically anything where you want to have personalization. So it's like the YouTube home feed, for example, has personalization to it. Your recommendations are different than other people's recommendations. Anything that has that personalization aspect to it in a really massive scale, they're probably going to want to use a vector index, to my understanding. So very apparently like a very common thing to anything that's scaled machine learning. And so then it's been hot over the last year, and so you're seeing stuff like this new database called PlanetScale actually forked MySQL in order to add vector indexes to it. And Redis, which likes to just implement absolutely everything under the sun, what the fuck, it also has vector indices. I don't like that Redis has vector indices. It's a cache. Why does my cache have vector indices support? That is rather crazy. But these kind of were like the earlier things to do it, I think. And then like these, I think, have come like within the last year. I think Phase has been around for a little while. I just read through the documentation last week. I think it's been around for at least a few years while these things just sprung up out of. I mean, I can't confirm that Redis did it within the last year, but it's just been so much more hot within the last year that it would not be surprised that decided, oh, hey, this is cool, a cool new index, cool new niche, database feature. Let's throw it in there. Yeah. Usually, if you need vector data, if you need this kind of thing, it's usually such a specific use case, such a specific access pattern that you would like know that it's going to be a part of your justification in your initial choice of the infrastructure for your services. And so you're going to just like know like, oh, I'm going to need a vector database here. You don't have it as like an afterthought, like where you wouldn't find yourself in a pinch with like PostgreSQL and be like, oh shoot, my problem is now a machine learning problem. Now I wish that I was not locked into PostgreSQL. No, you're usually gonna like know about this thing like up front because it's just so specific. Like you load these like embeddings into it. You're not gonna like have embeddings just kind of like come about and then be like, oh, I need vector indices because we have these embeddings, and like now we've decided to start trying to do machine learning stuff with it. Now you have the embeddings because you are doing machine learning, and so like you're gonna just know in advance this is a machine learning problem. We're gonna need a vector database, and then you're gonna pick it. So that's like, I don't know why you would ever use Redis as your vector database. I'd use something that like is much more like oriented entirely around handling vector data super efficiently. And so you probably use these. Yeah. Yeah, I don't even know what to think of this beyond that. It's really one of the latest things I've come across, and yeah, it's weird. Okay, let's move on. Data cubes and materialized views. Okay, so we talked about a database is a write-ahead log with a materialized view. There's actually this thing called a materialized view. It's for like speeding up stuff like count, min, max. There's also anything that's an aggregate operation in your SQL. So that would mean that this is a thing that involves doing a full table scan in order to compute. And so you can do these, you just pre-compute the whole thing once and then you store it in a certain way, and that's called a materialized view. I have no idea what the hell a data cube is, but it's out there. I've never used it. I've worked with OLAP stuff a little bit. I think it's if you're... It really seems like it's more of a thing that like somebody entirely oriented around being a data analyst would maybe make use of. But like these are things out there. You wouldn't have these on DynamoDB. It doesn't. You can't do. I don't think DynamoDB actually supports these operations. I'd be surprised if it does. It doesn't support joins. I'm fairly certain DynamoDB does not even have joins supported in the syntax. Most NoSQL databases do not support joins because it's like they don't do OLAP, and joins are a part of OLAP queries. And so similarly, it would just not make sense to have these in their language either. Like you don't have the keyword join in the syntax of DynamoDB or Cassandra, I'm fairly certain. And so then you can also just not allow these in the syntax because they would require a full table scan. And it's like, you're not using the database properly. So it's just not going to be there. If you want that kind of stuff, you should be using Iceberg and then just use Trino on top of it, or you can use Snowflake, or you can use, I think Databricks is working on it. I'm fairly certain that's another OLAP or data warehouse technology. So yeah, you're only going to find you have to use data warehouse or OLAP databases in order to get these indexes. You're not going to be able to just throw it onto DynamoDB. So I also wanted to talk about count min sketch. It's not actually an index. I'm fairly certain that count min sketch is not actually called an index. But if you think about RUM, if you think about that RUM conjecture, for count min sketch, like it's kind of making a very alternative trade-off. It's trading off accuracy for really fast OLAP queries, because this is from, these are all what you would call real-time analytics. And the word analytics, that's OLAP. That's real-time OLAP. When you execute an OLAP query, it's okay for it to take like 45 minutes. Under normal OLAP queries where you're working with a data warehouse, you're like, okay, here's my gigantic OLAP query, and like you're the only one using the database. It's not being smacked with like 10K TPS. You're the only one using the data warehouse, and you know it's not end user facing. It's not something that determines how fast your web pages are going to load. So it can take 45 minutes. But in some cases, you need to have like these numbers immediately. So like if it's a YouTube video where you want to see the view count for that video, the user is not going to wait 45 minutes for the web page to load. You need it real time. You need a real-time count. You need a real-time count for the YouTube video, real-time analytics. That's where this comes from. And you know, OLAP queries, they're usually really expensive. How in the heck do you pull off the kind of read speeds that you need here? You really need to make some interesting trade-offs in order to make those kinds of things run fast. I guess I think it kind of stores a materialized view, but it also does crazy, statistics things in order to make it work. And so that's why I think that you can kind of think of it as a very interesting trade-off in terms of the RUM conjecture. And then, not everything has... Fucking Redis has this too. I know Redis has this. I fucking know Redis has count min sketch. Why does it have count min sketch? Who gets a cache and then thinks, you know what I need here? I need some real-time counters. I need some real-time analytical queries on my cache. Why is that in there? That doesn't make any sense. Usually you have to pick a specific... Oh, I did already have Redis there. Oh, okay. I didn't realize it was even in there. Yeah, I did already type Redis. Yeah, what the fuck? Who gets a cache and then thinks, you know what? I can go ahead and I'm going to need some analytics, some really expensive OLAP queries here, and they're going to need a go just instantly. You usually like have a stream, and then you're going to attach this thing to the end of it. And so you're going to go ahead and pick a real-time analytics like product for it. You're not going to like just be like, oh shoot, I got this like database here. I sure wish I could do some real-time analytics on my PostgreSQL instance. You usually have to grab one of these specific tools, and then you're using it for that very specific access pattern that has arisen. There's a specific access pattern of, view counts on YouTube. It has arisen. You've already got your YouTube video thing, and then the PMs are like, okay, now we want to have this view counter, and so you just grab this extra infrastructure component and you're using that for the job. Again, very interesting trade-off in terms of the RUM conjecture. And I don't know if I had anything else for this video. I want to make sure that I covered everything that I wanted to talk about. All right, I guess that's everything that I wanted to cover. So I'll let you guys go. Thanks for watching.